Welcome to my presentation on the James Webb Telescope. Now that we have the first images released very recently, I'm thinking of making an event that is subsequent to my launch event. Basically, I'll be covering some of the things I covered in the previous event, but to give a context, this event will focus more on the first images, the details, what can we expect in the Webb's future, and so on. Welcome everybody. Thanks for joining me this evening. This is a CAP plus SSA event. The slides are from NASA, but I've customized them for our purpose. As I told you, we have a prequel to all this. There's an introductory event done by me, which is on the YouTube channel, on the CAP Group 2 YouTube channel. And then we had, at the time of the launch, we even had an SME talk from NASA's Christina Hedges. So she was from the Ames Research Center, and she gave an excellent presentation pertaining to the astrophysics part of the telescope as well. So the links are there. This is going to be a continuation of that. Some overlaps will be there, but I encourage all of you to actually have a look at those two videos as well in the future. I think people are joining slowly, and I don't have the controls to admit them. But if you have control, please do admit them into the presentation as well.
I'll keep an eye out for you.
Yeah, sure. Thank you. So moving on, I don't want to play the video right now. That's not my motive. Let's go to the next slide. So for today, I'm going to talk about these four things. Basically, I want to give you a quick recap of how Webb got to the place where it is right now. So where it all started, I have some pictures from the construction that was shared by my good friend, NASA Solar System Ambassador as well, when he visited the site at Goddard. And then we're going to see what happened after liftoff and the liftoff journey and what happened in between. Then we're going to jump in some theory and the theory about why we are studying infrared light, because this is predominantly an infrared telescope. And finally, we'll dwell on the Webb's first science images that we got very recently. So that's how we're going to start this event. But first, a brief video.
Is it mute or is there a voiceover?
Oh, there is a voiceover.
We're not able to hear it.
Yeah, I'll let it play, but
Without sound, interpretation is rather challenging.
Just to give a context, it was just an intro video and there was music running behind it. There was some commentary, but not really critical. They were just giving an intro to the James Webb Telescope and what it's capable of. So
that's all right. The visuals spoke for themselves.
You're muted, sir. Kailash, you are muted.
Unmute, sir.
I'm really sorry I was on mute. possibly that's why you couldn't actually hear the video as well. I can go back and circle. That should not be a problem because it's worth watching again. If you hear the audio, let me.
No audio.
No audio.
Okay, I'm going to jump ahead then. Let's not waste time. You're able to hear me, right?
Yes.
At
Yes,
the moment,
perfectly.
yes.
Yes.
Oh, thank you. So we are going back to the year 2016. This is when my friend Marty actually visited the Goddard Space Center to see the progress on the assembly of the telescope itself. So what you see here is basically the primary mirror before it was coated in gold. And this is in 2017 again. Things are beginning to take shape. In terms of the Webb telescope, the main element is going to be the primary mirror. You can see the coating of gold and the mirror looking in better shape in 2017. Another close-up shot. So this was years in the making, right? So it started somewhere around 2012. From 2012 onwards, we have been incrementally building this. We finally reached a point where we could launch this into space. So it finally happened on December 25, 2021. And my event back then would cover more details on that if you can catch up later.
Kailash,
You've been muted again.
You're muted again.
I don't know what's happening. I'm really sorry, but I'll keep the window open here so that it doesn't happen again. Okay, so now I hope you can hear me. So on December 25, 2021, we had the launch of the Webb telescope. It happened on an Ariane 5 rocket out of French Guiana in South America. Webb is basically the world's largest and the most complex science observatory. So it will be used to study celestial objects through infrared light. We are using infrared light because we can see much more greater detail and clarity than ever before. So Webb is the scientific successor to the Hubble telescope and the Spitzer telescope. It's not to say that we are going to scrap Hubble just because of this. Hubble is going, it has an ongoing effort and it has its own research purpose. There are two different telescopes, although we can say this is a much more superior telescope in terms of what we're looking in terms of detail. So because infrared light travels through dense gas clouds that block visible light, so we can see a lot more detail, not just in our solar system, but even in our universe. We can see distant objects such as stars, galaxies, other mysterious structures. So let's see what happened after the payload was sent into space. So basically, you can see the unfolding structure here, how the final deployment happened. And after launch, basically the final point was 1.5 million kilometers or 1 million miles away from Earth. So the destination was a point called L2. This is called the Sun-Earth Lagrange point 2. Basically, if you put an object there, it's going to remain there forever because the influence of gravity is going to be zero because of its position in space. So that is such a position where it will not experience any gravity from any of the celestial objects. That includes the sun, the earth, the moon, the other planets, etc. So if you see the blueprint, I'm just going to give you a small overlap of my previous presentation. So Webb was actually a size of a football field. So basically, half its area was the shielding, and the other half is the primary mirror. So that's the most area-consuming part of the telescope. Of course, we have the scientific instruments, which are very, very important as well. So just to give a background on Webb, Webb is a truly international partnership. So not just NASA, We have the Canadian Space Agency contributing as well. We have the European Space Agency. And then we have a body called Space Telescope Science Institute, which is basically conducting the science. And this organization is based out of Maryland. The lead agency, of course, is NASA. But it's very important to note that this is a very collaborative effort among 14 countries. So we have Austria, Belgium, Canada, Denmark, France, Germany, Ireland, Italy, the Netherlands, the Spain, Sweden, Switzerland, the United Kingdom, and most importantly, the United States as well. So it's a truly large-scale effort. And as I told you, briefly touched upon, there are two very big elements of Webb we were talking about. One is the mirror assembly, primary and the secondary mirror, and then the sun shield itself. Of course, we have the scientific instruments on the back as well. The lower part of the Webb is where the sun shield is. It's very important to actually eliminate a lot of noise. When we are viewing objects, it is very important that we don't allow noise from other elements disturb it. So that's basically the shield takes care of that purpose. One purpose is to block off light. The other purpose is to block off heat. So you need a lot of you need temperatures that are very, very low for this telescope to function, because this is an infrared telescope and it's very, very sensitive to temperature. So that the shielding basically takes care of these two elements, like blocking unnecessary light and then blocking the unnecessary heat. On both of these, more than 90% of it come from our sun. So that's our nearest source of light and heat. So we have to block all of those. I mean, a good chunk of those. Moving on. So just to give you the footprint of both the Hubble and the Webb. You can see Hubble is more cylindrical. It has a solar array that powers it, but Webb is slightly different. Webb actually works on solar panels, as well as we have a secondary energy source, which is basically not a nuclear reactor, but it's a nuclear powered kind of a device that powers the Webb telescope. As I said, Webb is really, really cold. The lower part of Webb, where the sun shield is, takes care of this. Basically, it's a field to protect light and heat, and it ensures faint infrared light from very distant objects are seen very clearly. So for this to happen, it is very important to locate the Webb science instruments in such a way that they are not influenced by the heat. So here are the numbers of, if you see the hot side and the cold side, you can see the temperature delta there. It's quite high. And the MIRI and NIRCam is one of the scientific instrument, and then the FSM and the NAR-ISS is another scientific instrument. Basically, these are two different kind of cameras or two different kind of scientific instruments to provide different images from different wavelengths, basically. So let's take a look at the Webb science instruments. So whenever I talk of science instruments, right, each instrument is actually tailored for a specific purpose. I kind of refer to the analogy of a Swiss Army knife, right? We have specialized components built within it for a specific purpose. So it's more like in that analogy. So while some instruments are more suitable than others for specific kind of targets, all 4 instruments on board can actually be used for a variety of investigations that make up our universe. So this does not limit us to anything. It includes universal objects that is such as planets, exoplanets, stars, nebulas, galaxies, clouds, whatnot. So these, if you can see here, this is the payload section. I jumped the slide again, sorry. So you can see there is a NAR spec there's an NIR CAM, there's a MIRI, and there's the FGS NIR ISS. So 4 instruments in all for different purposes. I briefly touched upon this, but you can see the orbit of the Earth with respect to the orbit of the Webb telescope. So this orbit is 930,000 miles away from Earth. What is important is the distance, right? So we are talking about a huge distance here for anyone to decipher. So communication is the key for everything, for all our science goals. So we have to leverage excellent communications back and forth. For that, we use something called the Deep Space Network. So NASA has satellites around the globe. I think one is in Goldstone, California. We have one in Australia, and I think one in Europe as well, to basically line up and communicate with deep space objects. Not just Webb, but there are other scientific instruments using the DSN as well. So it's not surprising to see Webb using DSN as well, because it's got an excellent track record. The command center is in Baltimore, by the way. And if you see the size difference, right, the primary mirror size difference between the Webb and the Hubble, the Webb is so much more bigger because we have to collect a lot more light from a lot higher distance in the Webb to obtain the kind of images that we are getting. So I'll leave it at that, but it's just a size comparison that I want to drive home. Why is Hubble's primary mirror pretty small? Because the applications are completely different. And coming to the next question is, why do we prefer infrared light over visible light? So as I briefly touched upon it, it's the quality of the images. Basically, they are higher in quality if you can, and you can go back more in time if you use infrared light, because it's in a part of our electromagnetic spectrum, which gives us more detail in the imaging. That's how it is. So if we design a near infrared or mid infrared wavelength capturing telescope, we can actually go beyond the red end of the visible spectrum. So that's the reason why you'll be able to see more. In a nutshell, that's why we're using infrared light. And there's also a concept called redshift, which I've touched on my previous presentation, where you can actually see how infrared light allows you to capture light years, objects that are light years away. By a concept called redshift. I will not touch on redshift in this presentation, but I've covered it in detail in my last one. And visible versus infrared light, you can actually see a lot more detail in terms of temperature. So these are animals in the forest. These are meerkats. So they are outside. They live on land. So you can see they are hotter. The other is a freshwater crocodile just out of water. So you can see that is far more lesser in temperature. So the same applies to the stars, but the distance, right? You can actually see which one is hotter, which one is colder, and which one is more recent. So that's why infrared light gives you an amazing new perspective. Because not all stars are of the same temperature. So you have stars that actually emit blue light, which is like higher than our sun, temperatures that are higher than our sun. There are other stars which are yellowish to red in color, which is of lower temperature. So it actually helps us to depict the kind of object in detail much more clearly. And you can also see the chemical properties and the atmospheric properties of the light that you are getting through the telescope. So you can make a lot more analysis with that. So basically, even in infrared, if you see you're operating across a big region. So James Webb actually covers the first 3/4 of the infrared region. We also have the Spitzer, which also operates in the infrared region, but it's not as far as where James Webb is right now. The Hubble actually is predominantly visible Also, it has some overlap in the UV and the IR region, but nowhere near close to what James Webb Telescope is. So what's important is beyond the red end of the visible spectrum, the wavelengths are longer, and the human eye can detect them easily. But the portion of this spectrum is predominantly infrared. So due to the longer wavelength of infrared light, we are able to pass through denser materials such as clouds and other matter that are there in the universe. So if you have a galaxy having a lot of nebula, so in visible light you will not be able to see beyond the dust, but infrared allows you that privilege of going beyond the dense matter to see what's behind it. So if you use a visible region, then you tend to use a shorter wavelength, which means your normal telescopes, like whatever we use in the visible region, cannot capture what's beyond. This is exactly the point I made in the last slide. So these are three different images of the same portion of the universe. So in visible light, although it appears beautiful, you can't see what's there behind the red curve, the red clouds. The NIR image is telling another story. So you can basically see through the dense matter, and you can see a lot more detail in it. And then there is the mid-infrared region as well, where to capture some other points like temperature and other things that you cannot capture in AR. So one of the things that you can do using the Webb telescope is to take a peek at the ancient universe, which means we are going all the way pretty close to Big Bang when the first galaxies were formed. So light from those galaxies are like so many million of light years away, but you can still capture them using the phenomenon called redshift, and the Webb actually gives you that image. So when we get to the sample images, I'll explain more on this. But it's all due to the Webb's sensitivity to infrared light that we can see the ancient light of the first galaxies, which has been redshifted as it travels towards the Earth over billions and billions of years. So light from the stars that is emitted as UV light and visible light, because of the distance, they get actually stretched into longer wavelengths, and that's why they are infrared. That's why you can detect objects that are farther away infrared. Moving on. So we have a lot more to actually learn from the Webb telescope as well, apart from whatever we have learned from Hubble. So basically, I was talking about the chemical composition of the object of interest, right? So basically, if you see the amount of sulfur, hydrogen, nitrogen, oxygen, these are all, I call them biomarkers. Maybe they can answer the question whether that celestial body or a planet or exoplanet was capable of or is capable of sustaining life in the future. So that's something that that Webb can actually help determine as well. So moving on. So this slide talks about splitting the light with Webb. How are we making analysis of what we see in the image? So what happens is spectra are hanging out behind the scenes, okay, and they provide an incredible amount of information. So we basically use a spectrometer or a spectrograph using the science instruments on board, so that the brightness of the individual wavelengths can be measured. So we can choose the wavelength that is of interest to us, and we can view that particular image. Although the universe is so big and there are other light sources out there, we can basically tune ourselves like a radio, right? You tune to the wavelength that you're interested in, and then you can view that object. That's how you kind of split what your object of interest from the others. So we have different type of spectrographs, basically, all for different purposes. Also, the Webb is the first telescope to have a multi-object spectrograph in space, which means we can get separate information about many objects like individual stars, using one image with one observation. So which means we can do a lot of post-processing within the instrument, taking one single image and analyzing it rather than taking multiple instances of the same image. So that improves a lot of efficiency, right? So this is a good time to dwell on the images that we recently got. They are really, really stunning. Basically, to give some context, these images will tell you what was our universe like shortly after the Big Bang. What are the characteristics of galaxies as the universe aged over billions of years? What more will we learn about how stars form, live, and die? We already know the science behind the life cycle of a star, but that can be confirmed practically this time. And also, there are a lot of unanswered questions, and we don't even know what questions to ask. We are in that kind of phase where we don't know the right questions to ask because we don't have enough data to frame our questions. So all those things will come into picture as we move along the journey of Webb, and the journey is like very, very exciting. So there are a few key things Webb will help us answer. So one thing is about the origins of our universe. The other thing is about the exoplanets and biomarkers, which I was talking about. And there are various other elements that new applications that we will find down the line as well. So now that we have our first images, why don't we take a look at them? This is Webb's first deep field image. So we have taken a cluster called SMAC0723 and it's oozing with detail. But let me give you a context. This is a tiny needle. This has no audio again. I'm going to play the video and you will see the amount of universe that the Webb has captured in its first deep field image. So zooming in. So this is the first image that it was released in the White House the other day. So this is the first deep field image. So this is just a small section of our universe. But you can see the amount of detail in the image. So these are all individual galaxies. You see some galaxies behind, light sources behind other galaxies because that's the beauty of infrared imaging. So you can go back, you can go to look through the clouds and nebula to see objects that are behind each other or aligned on top of each other. But they are two different objects from two different time zones, basically. The one and the other may be few light years away as well, more than a few light years away. So there's a bright star there as well. And then there are a lot of galaxies. Some appear to be blurry than the others because the gravity itself acts as a lens when you zoom in past a certain time frame. So your efficiency of the primary mirror is going to increase because gravity itself will actually bend the light for you. So this video was shared by my colleague Marty as well. So he went in, zoomed the image to show the detail that there is in the first deep field image contributed by the Webb telescope. This happened on this image was officially released on July the 12th in the White House. So just replaying again. Let's go to the next one. This is called South Ring Nebula. Before I give you a video of this, I'll just tell you what a nebula is. A nebula is nothing but a giant cloud of dust and gas in space. So nebula come from the dust and gas that are thrown by an explosion of a dying star, such as a supernova. However, there are other nebula regions. These are ingredients for new stars to get formed and also planets. So basically, these are stars or planets in the making. This is one such nebula that Webb has taken a photograph of. This is a much more close-up picture rather than the first one was a deep field image, but this one is like more focused. You can see the amount of detail there. So the same thing in mid-infrared light is going to look a little different. It's going to tell you which portion of that cloud is hotter or colder than the other. And basically the two dots you see there are new stars being formed from the clouds. And they are like in the process of becoming stars. These clouds have their own gravity, so they condense into a ball of star, or it may condense into a planet depending on the chemical composition of the nebula. We know all these through science, but it's good to reconfirm whatever we know in such great detail. And then the third one is the Stephens quintet. So this is an enormous mosaic of the largest image taken thus far by the James Webb Telescope. It covers 1/5 of the moon's diameter. It contains over 150 million pixels, and it's constructed stitching almost 1,000 separate image files. So just to give some context, this is how Hubble saw this particular object, and this is how Webb captured it. So as you can see, the Webb's picture is so much more larger. You can zoom into a lot more detail. This is an enormous mosaic. So the visual grouping you're seeing here consists of 5 galaxies, basically, and you can see the image captured both in NIR cam as well as the Muri cam. So you can see a lot of clusters, millions of young stars. You can see starburst regions, nebulas. Then you can see galaxies as well. And you can see the gravitational interactions among them as well. Let's wait for this to finish before I move on. This is the whole image again. The last one is quite spectacular as well. It's called Cosmic Cliffs. We have chosen another nebula. It's called the Carina Nebula. So what looks much like, it looks like the craggy mountains on a moonlit evening. It's actually the edge of a nearby young star forming region. So we call it NGC 3324. All these nebulas are named, by the way, by the astronomer who found it, or they have an ordering of how to name it. So we have a numbering convention going. So NGC 3324 is one such nebula, and the Carina Nebula is like assigned that number. So this is the Carina Nebula. You can see the size, right? The scale. So the line you see there is 2 light years. Then imagine the size of the picture. So this one is the Carina Nebula in near infrared. You can see the cliffs and the ball of dust and the stars surrounding that. So plenty of detail across so many light years. And light from this object is like each set of light is, I mean, at least like 4.8 billion years old, or it can, I'm told that Webb can actually go back 13.8 billion years as well. So on the deep field image, we went back like 4.8 billion years. I'm not sure. This is much closer, so this may not be like 13.8 billion years or something like that. The same in mid-infrared can reveal a lot more details. You see the colors of the stars. These are very important because, again, the colors of the stars will change depending on this temperature, right? So some are blue, some are yellow, some are reddish. You can see nebulas and the clouds and stars that are forming. And this is another part of Webb that is really exciting as well. So this is an exoplanet called WASP 96b. Basically, we capture an exoplanet when it passes a star. So we keep observing the star, and when this planet actually transits in front of the star, there is a dip in intensity of light. I know this is negligible from the visible point of view, but then that's how exoplanets are captured in infrared light. So if the intensity drops with an interval of time, so basically when the starlight is blocked by a planet, you can see the delta between the light observed and the actual light. It will give you details on the size of the planet as well, and sometimes even the chemical composition of the planet. So if you see the WASP 96b, it's one of more than 5,000 exoplanets that are present in the Milky Way. So we have around 1150. We've located these around 1150 light years away in the southern sky constellation Phoenix. And it's more likely a gas giant. And it has got no direct analog in our solar system. So we feel this is much lesser than the size of Jupiter, with a diameter that is probably 1.2 times greater than that of the Earth. If you see the temperature, likely it's like 1000 Fahrenheit there, significantly hotter. It's much more puffier than any other planet orbiting around the sun. Moving on. Yeah, this is a graph based on the that took the atmospheric composition of this particular exoplanet. If you see, water is a main key source there in the spectrometer readings. So this may be a candidate for biomarker. We don't know that yet, but depending on what science analysis has done over the years coming from now, we'll get to know more about this particular exoplanet. For now, we have made an observation. So this slide basically talks about how a star is formed, right? So these steps that are happening for the universe. So we can actually see the states from the beginning of free ionization till the present day, how these stars are formed and galaxies are formed. And this is probably, it was very difficult to visualize this before the Webb, but now it's like a lot more clear. This is again a Hubble image of a galaxy that was shown, that was actually there 400 million years after the Big Bang. So this is how we got, this is the furthest we got with the Hubble. Of course, with Webb, we can now know that we can get a lot more deeper. So one of the things we do is like we can observe galaxies over time using the Webb. The other thing we can do is dissect black holes. Basically, Webb will study black holes both near and far, both in our own Milky Way galaxy as well as the planet itself. So in nearby galaxies, we can use the spectrometer to learn about the temperatures, speeds, and compositions of the materials regarding the field which we're interested in. So, for example, if you take the Sagittarius A star, there is a supermassive black hole that is present in our galaxy. So, basically, if you can focus more detail on that star, we'll be able to learn a lot more regarding the black hole as well. So usually whenever these black holes are present, there are powerful jets of light actually coming out of them. So that's one of the indicators of a black hole. No one, like, until recently, a black hole has never been imaged. The other thing is Webb will also study stars in detail. So many other stars, how they form, live, and die. This is something I've touched on as well. And this is something I've touched on as well. We can detect molecules in star forming regions. So basically, I showed you the chemical composition slides. And within our own solar system, we can actually get a lot more detail as well. This is Jupiter and near infrared. So it will show a lot more atmospheric content than what our present instruments are showing as well. It can. One beautiful thing with these instruments is we can validate a lot of science because there is a separate probe that is actually around Jupiter as well, orbiting around Jupiter to gather data from it. So if you can take the science and validate whatever we study, that's another point of validation for us. And Webb will definitely help out with us. And finally, infrared light helps us find distant objects. So exoplanets, in this case, as I already told. And we can go a step further by decoding the atmosphere of planets. That's basically it. I've touched upon all the things that Webb can actually do, and the first images confirm that. Now is a good time for questions.
Kailash, this is kind of a basic question. Most of the Webb shots of space showed some high-intensity points. Almost all of them appeared to be with 8 radiating arms. Is there a scientific explanation for why the arms, or is that an artifact of the sensor?
Oh, that's an artifact of the sensor, I think.
Okay, so the sensor may be overloaded in some mode, which is why it shows.
Yeah.
Got it.
Question, Lieutenant Alexandros. There are 2 ways that you can end up with infrared light from space. One is if the object is very long distance away and the expansion of the universe is stretched the wavelength.
That's
the
correct.
other is it could be close by and just radiating at that particular infrared frequency.
Yes.
So that says there's most of the universe. There's infrared radiation coming from most of the universe in between us and a very distant object.
Correct.
How do we see through all that blockage, so to speak, to determine that something is, say, 13 billion light years away? They're at the same frequency, they're both in infrared. And as I say, there's a tremendous amount of stuff in between us and that distant object.
Correct. So the wavelength, if you see the bandwidth in the infrared region, it's a lot more than the visible light. So visible light is just a tiny band of wavelength. If you see the infrared, it's more spread out. That's why we have different scientific instruments on board to analyze different infrared wavelengths, basically. Not all wavelengths, infrared wavelengths are the same. The range is quite different. And of course, we have the ability to select the exact wavelength we want. We can fine tune it. So to answer your question, we can take the object of interest, fine tune to our wavelength, and then eliminate the noise, basically. The others are just noise.
But you would still, if that object of interest was, say, 13 billion light years away, you would pick a specific wavelength because it's receding at a very high speed. So you would pick a wavelength and match that recession velocity. But there's also a lot of matter in the between that might also be radiating at that particular frequency, even though it isn't receding very quickly. So I guess what I'm thinking is there must be a lot of blockage. Even if you use a narrow band of the sensor, there must be a lot of blockage preventing you from seeing things that are at the beginning of the universe.
I don't know how to accurately answer your question, but there is a mechanism to do this. I can probably ask the SMEs how it's done. I get your question, sir, but I don't have any more details on it right now.
Okay, that's thanks.
Kailash, another way to ask the same question is most objects have some reflective capabilities. So I now have a large number of radiating objects in the field in front of me. And as they radiate, re-radiation occurs, different timing and all the rest of that. But it's the same problem you get in radar. It's the ground scatter, the backscatter problem. How do you eliminate the moving from the non-moving, et cetera, et cetera? You do it by wavelength analysis.
True, we do it by wavelength analysis, and that's all I know about it at this point. I don't know how are we going to manage the signal to noise ratio as well. That's another aspect.
It's Tony Sue here. I've got a question about the positioning of the Webb telescope. You mentioned, I think, that it's at the Lagrange point and that it doesn't move around, but I would assume there is some drift possible. So are there correctional, the directed jets that can reposition the telescope if it moves?
I'm not aware of a retro rocket system present on the telescope because they are pretty confident that L2 is a point where there is least disturbance from any gravitational pull from any object. So
yeah, I suppose even if it drifts a little bit in the various directions,
yeah, but so how much does it drift over time? I'm not sure. I don't have a detail on the drifting capability. But what I do know is I don't think there is a retro rocket kind of firing to put it back into orbit. We don't have that.
Okay, thank you.
Yeah,
thank you.
In fact,
is a heat source.
I have a quick question.
Yeah.
Excellent presentation. I was wondering if in the program, if there's any emphasis on possibility of discovering any new elements. I mean,
oh, this is very, very interesting. We don't know any new elements that have been discovered because of Webb, but it's certainly a possibility. As I told you, right, we don't know a lot of right questions at this point. We don't know a set of right questions that can be asked. So this is possibly falling into that category. We always keep discovering new elements. I mean, over the evolution, our periodic table has been like I won't say multiplying, at least get added on at a constant rate. So we will get into that situation where we get a wavelength or a spectrometer reading that is not consistent with any of the periodic table elements, and then we kind of discover a new one. Very much possible.
So a red flag comes up and someone gets to name it.
Yeah, exactly. Which is fairly consistent, but it's not matching to any of the elements that's present in the periodic table or any of the compounds.
Thank you very much.
Yeah.
And Lieutenant, I just put a quick quote from the James Webb website regarding the onboard systems for course adjustment.
Absolutely, that's awesome, Commando Guest. Because I didn't know if there was a retro rocket system or not. That was an excellent question.
Yeah, it's got two systems. One uses hydrazine, the other one is dinitrogen tetroxide, and it also has reaction wheels.
Sure. Thank you for confirming that. Good, Captain West.
Looks like Lieutenant Chifalo has a question.
Oh, I already asked the question. I just had my hand up. I just brought it down. Thank you.
What is the expected lifespan of the telescope?
We don't know yet. Honestly, these Webb instruments, at least they have a decade of power left in them. But it all depends upon the when the juice runs out, in the nuclear system. So it's going to be like beyond the official 1 decade or something that they've confirmed initially.
And I suppose there could be some decay in the image quality over time with particles that strike the telescope mirror.
Yes, that's one thing which we have to worry about as well. But Lagrange 2 is actually a pretty safe point where it's like it's not susceptible to any kind of foreign object hitting it anytime soon. So I believe it's a safe point in terms of that.
Good. Yeah. Thank you.
I have one more question. The area that it's in, apparently it's zero gravity or zero gravitational pull, or the least amount. Are the systems within the telescope, did they take that into consideration when designing the systems as far as to operate in a zero gravity?
Not just zero gravity, but the conditions you get at the Lagrange point L2, everything has been simulated here. Data has been simulated as of like whatever we're going to observe, we're going to observe in an environment that is analogous to what we get Lagrange point 2. So to answer your question, L2 is where the telescope will operate with its most efficiency.
Thank you.
And to answer the lifetime question, the James Webb Space Telescope carries enough propellant for approximately a 10.5-year mission, assuming that the on-orbit performance matches what was simulated.
Yeah, it's again, we put a number to it, Captain West, but we normally exceed it by multiple folds. Normally, that's our experience with the Mars rovers as well. And considering there are no moving components like the rover, I think we can pull on a little more, or a lot more. But time will tell that. But yeah, definitely.
Another question. You mentioned there are no moving components, but are the hexagonal mirrors, are they not adjusted individually?
Oh, they are. By moving components, I meant like a rover, wheel system, thing to plug through. Yeah, that's what I mentioned. But of course, their mirrors are adjustable. Yes.
And how are they moved? Are they small pieces?
Yeah. So if you see the primary mirror, right, you can see a lot of individual hexagonal elements there. So each individual hexagonal element can be actually rotated or put into a position that's desired to get the maximum output of a collated lens, basically.
And what is the motive force?
Or not lens, mirror, rather. Sorry.
What is the motive force for that?
Oh, I think there will be some motors, definitely.
I see. Okay.
Yeah.
I'm assuming maybe it has some sort of zoom lens, or is it such high definition that it digitally zooms in?
Digital zooming is definitely there, but you can control the angle of the mirrors to basically control magnification as well. So that was actually done during the time between deployment and the first images. So basically, they had calibrated it to an extent where it produced an image of this quality.
Question for you about communication systems.
Pardon?
This is a question about communication systems. When Webb calls home, is she being driven by nuclear power or photovoltaic, some form of solar power, if you will?
So I don't think solar power will be adequate at that distance. So I believe there is some kind of nuclear power there to power the telescope over a decade or whatever the time span is. If you see the Hubble, it's much more practical to use a solar panel, but this one is way like deep into the solar system. So I believe there is a nuclear component to it.
Okay.
And the location will minimize any sort of debris, space debris that it might compromise?
Yeah, that is the whole idea of choosing this. L2 has been chosen really carefully. So basically, the odds of some foreign object interference is like is reduced.
What frequency bands are used when it does call home through the Deep Space Network?
Oh, I'm not sure about the frequency bands that are used, but there is a resource where there's a website where you can see what communication is happening and where with the Webb telescope. I'll post a link possibly later in this presentation as I conclude. So you can see where the deep space network satellites are actually communicating. There are a lot of instruments, not just Webb, right? You can see when that is happening, and from that, I think you can get the frequency.
Thank you.
Actually, this is there in my in the other presentation where the NASA SME Christina Hedges from NASA Ames actually addressed this very question. So she opened up the page, the web page for the Deep Space Network. Let me try it right now.
It's in the chat.
Oh, it's in the chat. Okay. I'm trying to get to the chat, but I can't. So I'm going to quit this presentation so that way it gives me more control. Okay, there you go.
Doesn't look like Webb is phoning home just yet right now. Mars Reconnaissance Orbiter is, though.
Do you have the screen? If you can share it, Commander West, that would be great. Because I'm going to unshare mine. I have to load the web page as well. So since you already have it open, why don't you? Yeah.
Okay, can we see it?
Yes. So right now, if you see the one in Madrid is communicating with an instrument, the one in Canberra, Australia is actually communicating with something called SOHO. And Goldstone, surprisingly, none of the communications are active right now.
So rather than relying on the orbit of the satellite, it's the Earth's rotation that's going to determine the communication area of the Earth.
Exactly. So that's we are also rotating, right? Every 24 hours we have been rotating. So not one single dish can capture the entire area. So that's why we have 3 different dishes basically to communicate to different objects. Yeah, 3 different locations on Earth.
Yep, Curiosity is calling home too.
Yeah. And surprising, Curiosity is still active, doing a lot of work.
Doesn't surprise me at all, considering Pathfinder, Spirit and Opportunity lasted forever.
Yeah.
Kailash, could you just review quickly the instruments on board, please? I know there's some near-infrared instruments, but there's also one, the abbreviation I didn't know, G something. What was that?
Oh, there's the MIRI, and let me see the other one. Just a second. MIRI is the mid-infrared.
I see.
Then,
okay.
Yeah, and then if I go to that slide, what's the other one? There are 4 in total. Just give me a second. I'm just getting to that slide. I don't remember the exact name of the 4th one off the top of my head. So yeah, there's the near infrared spectrograph, and then there is the MIRI, and the third one is called the NIR spec. Which is called, that is the near infrared spectrograph, and then the NIR cam, and then the MIRI, and then there's something called the FGS NIR-ISS.
Yes, that's the one I was wondering about.
I basically don't have too much information on that.
No
It's called the Fine Guidance Sensor. FGS stands for Fine Guidance Sensor. But I don't know what exactly is the science behind that, because I really honestly I've not taken the the right questions from them basically. So I will not be able to answer what's the Fine Guidance Sensor doing. But
I assume that's some kind of image analysis system that allows the telescope to point in the right direction.
I dropped it in the chat.
Oh, thanks. For some reason, I can't see the chat.
I know there's certain elements in the universe that are conducive to life, as far as elements and gases and what have you. I know the spectral imagery with the planets in that area kind of will give you an idea of whether nitrogen based, what it's emitting, what type of elements are going on. Are there areas that they're focusing on that are more conducive to, I guess, creation of possible life or what have you?
So basically, we try and spot exoplanets. So that's where the first starting point is. So once we zero in on the exoplanets, what we then do is we try to see the biomarkers. Basically, they are the life signs, maybe the gases like oxygen, for example, or say carbon dioxide is another biomarker. So if you can get anything from the spectrograph with these biomarkers, those would be our primary suspects, right?
Kailash, it would be good if most of us could see the chat. I think a lot of people, myself included, cannot see it.
I'm getting to the chat. Yes, I am seeing it right now.
But what about the rest of us that can't see it?
Okay, so there should be on the top, there should be a button called chat.
But it's not visible to many of us.
It's tricky.
Yeah.
Let me share my screen again. Let me share my screen again. That way, I think you'll be able to see it, at least.
I can also package up the links and I can send them to Kailash for distribution.
I can do that as well.
I have a button called chat, but I cannot see anybody else's chat besides my own.
I have it under, it's a little thought bubble. Those little bubbles that come up that you have a thought. That's where my chat is under.
So Captain West has shared information on rocket thrusters and propellant. Apparently there are. My apologies, because I haven't read much on that. And then a lot of other information as well. There's a link to the web page that Captain West just opened, ice.nasa.com. And then the instrument, the NIRCam and the NIRSPEC and the other instruments.
So besides from the Deep Space Now, which is eyes.nasa.gov, all the links I've been going to is web.nasa.gov and pages underneath that. So if you want information about Webb, that's probably your best place to go, web.nasa.gov with 2 B's.
Yes.
Kailash, I think the answer may be how we were admitted. If you're admitted as a guest, which I think I was, you can see chat.
Oh, you wouldn't see chat. Okay. So, I didn't know how Teams work. This is the first time I'm recording in Teams as well.
Yeah, it doesn't seem like there's any information in our chat on Teams. I think you might have to share it on your end as the presenter.
Sure. I will. What I'll do is I'll take an export of the chat and then I'll send it out by email to everyone. Copied it already. So after this meeting, I'll just send out an email on the resources as well. Of course, the aim is to use this meeting as an external CAP event as well. So that's the reason why I'm recording. Maybe we can trim the video and put it in our YouTube channel for future viewing.
Right now, we're all enjoying the Oshkosh approach video.
Oh, that is really awesome. I don't know. Is that your screen, Captain West, or is it? Oh, it's
That's
Captain
not mine.
Williams. Captain Williams.
Ron Williams uses that a lot.
Yeah. It's amazing. So unless we have more questions, I think we can wrap it anytime you want to. But I'm open for questions.
Well, I just want to say thank you very much indeed. It was a great presentation. Really
Thank you
appreciate
so much. This is a stock presentation that I got from the Webb team, but I customized it to the extent possible. So you cannot credit me with all the slides, maybe, but I added my own stuff here and there.
Yeah, but thank you for showing.
Well done.
I really appreciate that. Thank you.
Thank you.
Thank you, everyone.
Thank you. Good night.
Good night. I'm going to stop the recording first.